Greetings and welcome to Hobo University, where your professor will teach you what you need to know to get started with solar, batteries, and understanding electricity. In our previous lesson, you learned all about volts and how voltage is important. Today's lesson will focus on what are amps, what's amperage, and why are they important to understand. So if you haven't watched the previous lesson about voltage, there's going to be a link on the screen and in the description of that video. You're definitely going to want to follow up and watch that too, as this is a multi-part series. By the time you finish this series, you should have all the answers to all your questions regarding these concepts. So let's get started.
HOBOTECH.
So the question is, what are amps? Why are they important in electricity and electrical circuits? So just like the unit volts were named after the physicist that measured them, Alessandro Volta, amps are also named after a physicist, and in this case, the one that formulated the law of electromagnetism called Ampere's law. His name was André Marie Ampere, and in English, we shorten this to amps. Note that amps and amperes are interchangeable and refer to the same units. Now, what is different is the word amperage. Now, notice there is a difference between amperage and amps. Amperage is the actual measurement of the flow rate of the current in amps. So amps is the actual unit. Okay, let's return to the drawing of Pascal's barrel experiment where we learned about voltage in the previous video. Now quickly, I'll explain this again. You have the barrel with the pipe. The water in the pipe is creating pressure. It flows from negative to positive. In this case, we're using gravity as an example. The water flows into the barrel. When the barrel fills up, you keep pouring water and eventually the barrel explodes due to the pressure. So the difference between negative and positive is what we called voltage. So that's the difference in pressure. So you may recall that I briefly mentioned in the previous video that the size of the pipe in this drawing, in this case, we're talking about the actual width of this pipe, the inner diameter of this pipe, would be considered the same as amps in this concept. So let's elaborate more on what are amps. The voltage is the difference in water pressure, as I mentioned before, and we consider the top negative and the bottom positive because electricity flows from negative to positive. Amps are then represented as the width of the pipe. As then we would logically assume the higher the water pressure or the volts and the bigger the pipe or amps, the more total water is going to flow into the barrel per second. And in electricity, that flow would be called amperage of the circuit, or the strength at which the electrons or water in this example flows. Now, if you know about volts and amps, you might already know where we're going to go next. So if you want to figure out the total amount of energy flowing through the pipe, it's a pretty simple equation. You take the volts, or pressure, that would be going in between these 2 points, and then you would multiply by the amps, or the width, so this would be considered amps, and that's volts. So volts is the strength of the pressure, amps is the width of the pipe. So you simply take amps times the volts, and you get the total pressure in watts. Most of you guys watch this channel have heard of watts, maybe even know what they are. This is the actual formula that you use in electricity. So you take the amps times the volts, and you get watts. It's that simple. And guess what? Watts are also named after a real person, this time an inventor who made significant contributions to the development of the steam engine. And you may have heard of him before. His name is James Watt. However, we're not going to cover Watts today as they deserve their own video. So back to the diagram. There's one concept we're still missing here that needs an honorable mention. And this is called resistance. Now the resistance is measured in something called ohms. And you guessed it, it's named after another physicist, George Ohm, who came up with Ohm's law. See, in a perfect universe, these pipes, which represent electrical cables, would be perfectly smooth inside, friction-free, and in a total vacuum, allowing electricity to flow unimpeded with no resistance whatsoever. This, however, is not real life. In fact, there's no such thing in nature as a substance that allows perfect flow of electricity without some kind of resistance. However, technology has provided something that is called a superconductor, and these do exist, but they don't exist at room temperature, at least not yet, and they require super cold stuff like liquid helium to work. If you've ever had an MRI or magnetic resonance imaging scan or rode a maglev train, those use superconductors, and they have to be constantly cooled all the time for them to work. This means inside all electrical conductors, there is resistance. Resistance is futile. Now you can imagine that instead of being filled with something slick like water, They're instead filled with something like honey, because as we all know, honey is very thick and it's very difficult to make it flow. Imagine the pipes are filled with honey. That is the concept of resistance. And of course, the thicker the honey, the higher the resistance is going to be. So what would be considered a regular conductor of electricity? Well, this is going to be all the metals on the periodic table. So my understanding is everything that is circled has some form of conductivity with electricity. So most of these metals are not very good conductors, and very few have the right qualities to be electrical cables or wires, like malleability, ability to resist corrosion. Some of them just crumble into your hand. Some can't be exposed to oxygen. Some of them are radioactive. So in order to make a good cable, there's only a certain number of highly conductive metals on this chart, which would be easy to make cables into. You may already know that the most common metal used in electrical wiring is copper. That is Cu right here on the periodic table. So you may just immediately assume copper has to be the best because it's used in everything. However, copper is actually the second best conductor of electricity behind what's right below it, silver, which is Ag on the periodic table. Silver is actually 7% better at conducting electricity than copper is. Silver being 7% better at conducting copper, you're probably wondering, why don't we just make cables out of silver? Well, that's pretty obvious because silver is way more expensive than copper. In fact, as of the filming of this video, copper is about 25 cents an ounce, where silver is about $30 an ounce. Silver also tarnishes very easily, but copper isn't without its issues. As many may know, the Statue of Liberty is made of copper, and when they restored it back in the 1980s, the new copper was shiny and not green like it looks like today. Copper too corrodes when exposed to the atmosphere and will turn green and eventually crumble away. The next best conductor is, again, right below it. Isn't that funny how that works with the periodic table? Au, give me back that gold. So gold is actually one of the best conductors. But again, we're talking $2,600 an ounce right now compared to silver's $30 an ounce. One major benefit to using gold, it doesn't corrode at all. It's one of the reasons why the Egyptians use it, and it's coveted so much because you can expose gold to the elements for millennia and it never corrodes, unlike pretty much everything else does. I don't think there's nothing else here that doesn't corrode except for gold when exposed to the atmosphere. Gold is actually used inside of computers and other electronics. Sometimes copper conductors are coated in gold so that the connection resists corrosion. Now, another metal that has started to make a comeback as an electrical conductor isn't really that great of a conductor compared to copper, and that is aluminum. Aluminum is only 61% of the conductivity of copper. However, at only 7 cents an ounce, or about a third of the cost of copper, aluminum is actually used in large power cables. So when you look up and you see the cables that are running across the country on those big towers, those are made of aluminum because it's so much cheaper and it's only 30% of the weight of copper. So you have lightweight, much bigger cables, much cheaper cables running high tension lines. Now, one of the major issues using aluminum, especially in a solar build or using it in your home wiring, is that they need to be virtually double the thickness to transfer the same amount of amps, and that can be problematic because a lot of solar charge controllers and some inverters only have connector lugs of a certain size, and those are designed for copper. If you try to stick an aluminum cable in there, it's just not gonna fit because the cable would have to be almost twice the size to transfer the same amps. Also, aluminum has a much lower melting point than copper, meaning if your aluminum cables overheat, they have a much better chance to melt and cause a fire. So I always strongly recommend that you use quality copper cable in everything you do when it comes to batteries, solar, inverters. Don't ever cheap out on your cabling or you may end up paying the price later. I've actually seen folks using like aluminum speaker wire cable to wire up batteries and solar panels. Don't be that person. So why is resistance important and why do you want it as low as possible in your build? Because resistance inside of each cabling that's too narrow for the amps required, can overheat and melt. A good example of what you've seen for many years of your life is a light bulb. And the reason why a light bulb glows is because of resistance. In fact, resistance so high, the wire glows burning hot, but since it's in a vacuum and made of tungsten, the actual element doesn't burn out, it just glows super bright. So the actual element inside of the bulb that glows is very high resistance. You don't want that happening to your solar build or your batteries or any wires in your home or your RV or your car or wherever else you're building. That ever starts to glow because of too high resistance, the cables will melt and will eventually catch fire. So how do you know how thick of cables do you need to prevent this from happening in your build? We have to look at something called ampacity. So think of the word capacity, but it's for amps. So it's the amp capacity of a cable or a wire. So you're running some cables for your solar. You would come to my forum on Facebook and say, I would need to know what wire gauge I should use for this particular situation. What ampacity do I need? So that's what you want to ask. And ampacity is actually related to how thick your cable is. So say you have two cables here, one is 2 gauge, one is 0 gauge. They are different ampacities. And the ampacity isn't just the width of the cable, but also the sheath that is on the cable. So say this 2 gauge cable has a special highly heat resistant sheathing on it and this one doesn't. The ampacity of this might actually be, say, 40 amps, and this one might be 40 amps. Even though it's a bigger cable, the sheathing on it maybe can't handle heat where the sheathing on this can. Therefore, it actually is a smaller cable that can handle higher amps. Now, I'm not going to get too technical on this, but one of the best wires you can use in the market for running solar or electricity in your home, stuff like that, is called THHN. And a lot of people just call it thin. THHN, don't remember off the top of my head what this stands for, but this is actually the shielding on the cable. And a lot of these, like for example, I have a 6 gauge cable that I use for a lot of things, 6 AWG. That stuff's good for 90 amps. Where if you didn't have the thin cable and it was just a regular rubber casing, it might only be good for 60 amps. So that's a major difference in amps for the same size cable. Of course, this cable is going to be a little more expensive, but think about it. That actually means you can put more power through the same size cable and you're paying for less copper. It's not just the thickness and the sheathing of the cable, it's also if it's stranded. Most of you already know what this means, but I'll cover it anyway. If you have a solid cables is usually what is in the walls of your home. Most of the Romex, it's all solid cables. Stranded is a bunch of little strands that are all wound up together. Now, I know those look exactly the same, but assume this one is a bunch of strands of wire. Okay, we'll do it this way, make it simpler. That's a whole bunch of strands of wire. This is actually just completely solid. Okay, so you got a solid and a stranded. Those are going to have 2 different ampacities because stranded wire carries different amount of electricity for the same thickness as a solid wire. All right, let me give you a couple of examples on what wire gauge and ampacity means. So for example, we have a solar panel here, which would run typical PV cable. PV stands for photovoltaic. I just say it's solar cable, but if you go in and ask for solar cable, they might scratch their head. It's photovoltaic or PV, so we'll call this PV. So you have PV cable coming out, and most PV cable is going to be 10 AWG. Now, yes, you can get 6, 8, 10, 2. You can actually buy your own cable, but most of the cable on the market is going to be 10 or 12 gauge with a special UV coating on it that allows you to just throw it on the ground outside or throw it on the roof and pretty much last for many, many years before that cabling falls apart. Most of it is 10 gauge, 12 gauge, 8 gauge. 10 is the standard. But a 100 amp battery, so this is a 100 amp lithium battery, lead acid, doesn't matter. 100 amp would actually require a much thicker cable. This is going to be huge compared to this, would be a 2 or a 4 AWG. Now, the lower the number, the fatter the cable. Why they did it that way, you have to read up about it. So 10 gauge smaller cable was what you'd use for solar. 100 amp would require 2 or 4 gauge. Now, why did I say 2 or 4? 4 is if you're running a longer distance. Say you're going to run it 30 feet. You'd want to use 2. If you're going to run it only 10 feet, you'd use 4, because think of resistance. The longer the run of your cable, the higher the resistance. So if your cable is running 50 feet long, let's do this example real quick. You have a cable that is 50 feet long, okay? Then you have a cable that's 10 feet long. Think about that honey example where these are filled with honey. it's going to take a lot more force to push that honey all the way through 50 feet than it will for 10 feet. Now, the resistance of these two cables are actually going to be different because they're different lengths. Even though they're made of the same exact material, the 50 foot is going to have more resistance because it has to push that electricity much longer distance. And for every inch it runs, it uses a little bit more power. It wastes a little bit more power to heat. The shorter the cable, the less heat has to come out of the cable. I'm making this simple, by the way. And therefore, you don't have to use a stick of a cable. So in this case, the 50-foot cable might be 2 AWG or 2 gauge, where the 10-foot cable might be 4 gauge. So that's the difference when it comes to cable runs. You got to make sure that you have a thick enough cable gauge for the length that you're going to run. But say you're running something massive, okay? So say you're running a 15,000 watt inverter. So you have a 15 kilowatt for 15,000 watts inverter. So let's say that pulls 250 amps. That's way more than we're talking about over here. Over here, we were talking about a couple dozen amps. Now we're up to some big boys, 250 amps. You may use what's actually called 4-aught cable, and that's a 4/0. And what that means in electrical terms is 4 zeros, or what we call 4-aught. So 4-aught is going to be a pretty large cable. In real life, if I'm drawing this on screen, it's probably close to this thickness right here. It's a pretty big cable. It's almost this thick in real life if you include the outer casing on it. And that's the kind of stuff you have to run into these inverters because they have giant lugs in there because they know you're going to be pushing tons of amps. Your battery bank down here is going to be very likely a 48-volt battery bank. It could be 200, 300, 400 amp hours, depending on what you decide to purchase. But that needs to go into here, and it's going to pull hundreds of amps. So it all depends on your inverter. I use this example, 15 kilowatt. It's probably closer to 300 amps for 15. So say a 12 kilowatt would be around 250. I'm just doing the math in my head. So with a little bit of math, very easy math, I can tell you if I am correct on there. So we do 48 volts. A 48-volt battery actually runs nominal about 50 volts times 250 amps. So 50 times 250 is 12,500. So that would be watts because we learned earlier you take volts times amps to get watts. So if you have a 12 kilowatt inverter, in this case I should have made that a 12 instead of a 15. If you have a 12 kilowatt inverter, you would have to get 250 amp cables for it because a 48-volt battery runs nominal around 50 volts. I'm rounding off. And if you're not sure, always go up a size. So say this 250 amp cable, the Ampacity chart says that you need to run 3-aught cable. I actually would, because I personally like to oversize my cables to be safe, you can actually put a bigger 4-aught cable in there. Yeah, it's going to cost you an extra 20 cents a foot, maybe to go from here to here. But if you're only buying 10 feet of it, that's really not anything, right? Now, if you're buying 300 feet of it, that extra 20 cents a foot is going to cost you extra money. And in that case, you may decide just to go with whatever the chart tells you. I almost always go one size up from what the chart tells me. And what does that chart look like? Here you go. This is one of my favorites. I like the color coding of it. Now, I will quickly describe to you what this is. You can basically search for, this one actually says DC wire selection chart, but this particular chart is actually used on many websites. So let me explain this to you very quickly. So it says over here, you pretty much want to use this 3% voltage drop for critical loads. You can use the 10% if you want. What this means is that over the distance that you specify, you are allowing a 3% voltage drop. So for solar, you probably want to stick with 3. You can go with 10 for non-critical loads like light bulbs and things like that, but I like to stick with the 3% drop. So say you need to run round trip a 20-foot cable, and you want to know at 20 feet, how many amps can I run for a certain gauge? So the 250 amps that we talked about is not on this chart. Let's stick with 100 amp batteries. So say we want to actually be able to pull 100 amps from a battery, follow the 20 feet all the way across to 100, which is right here. And where this meets, it says 2 gauge. So for a 20-foot cable, dropping 3% voltage at 100 amps, you use 2 AWG. So you can use this at your own time and check it out and see if you're running solar, you may be running a 100-foot cable for solar. And at 100 feet, you might want to do 20 amps because 20 amps is typically what a solar cable would require if you're running it over a long distance. So at 100 feet, 20 amps, it says right here, you're supposed to use a 2 AWG. So you can see here that running very long distances requires you to pretty quickly use a lot larger cabling. Okay, there's something very important to understand about amps that is different from volts. Amps are pulled from what's available at the source, okay? Voltage is actually pushed. So this is why amps on an input to a load doesn't matter. Only output from a source matters. So what do I mean? Okay, so say we have, this is actually a cable. So this is the top of a cable that's running down to some load. So say down here you have some amount of loads. So in this case, you can take this 30 amp cable and run a 30 amp load. This one would go off to a 15 amp and that one would go off to a 15 amp. So let me explain it another way. Okay, so here you have a solar power station. Okay, it's got a little handle, it's got a little display. This is your Jack Eddy, right, which has a solar input on it, an MPPT. So say this solar panel can output 20 amps, and the Jack Eddy input can take 10 amps, and that's pretty standard. A lot of them are 10 amps or 12 amps. Well, you're looking saying, okay, well, 20 amps is going into 10 amps. Isn't that going to blow up my Jack Eddy power station? Absolutely not, because in this example here, we had 60 amps, and it's only going to pull up to 60 amps from the source. But each circuit on this is a 30 amp circuit, so it's only going to pull 30 amps. In this case, this is a 10 amp circuit because the power station is considered a load on a solar panel. Solar panel is setting power into the Jack Eddy power station, and even though 20 amps are available, the Jack Eddy can only handle 10 amps. So it cannot pull more than 10 amps. So no matter what you do to this, you can put 200,000 amps. Let's say you want to put 200 kiloamps into the Jack Eddy. It's only going to pull 10. So I get this question almost every day, sometimes only 3 times a week. If I have a giant solar array with 10,000 watts, can I put it into my power station? If I have a 60 amp DC to DC, can I push it into here? Is it going to blow it up? Answer every time is no. Say your Jack Eddy can handle 30 to 60 volts, and this solar panel puts out 40 volts. That's within this range. So 40 volts fits in that range. 10 amps is its maximum, so it's going to actually pull, in this case, and we can just do the math real quick. If the solar panel outputs 40 volts, and it can only pull 10 amps, guess what? Your power station is going to pull 400 watts from this solar panel, so assuming the solar panel can provide 400 watts. But we're saying 40 volts at 10 amps, 400 watts. Remember, we did this math earlier in this video. You should now have this equation memorized and mastered. Let's go back to this drawing real quick where I have the 60 amp broken into 3 circuits. Now, this is what would happen in your home or in a car. Because say you have an air conditioner, because air conditioners would take a lot of power, maybe that's your 30 amp circuit, okay? This might be your lights. This might be your refrigerator. Now, the difference in this is that right here, you would have your circuit breakers. Okay, so you have a circuit breaker here, circuit breaker here, circuit breaker here. This would be your house wiring coming in from the grid. So say you have a 60 amp box, you can break that out to 30, 15, and 15. So you have your AC on the big one, your lights, and your refrigerator on the other ones. So again, this works for your house too. This isn't just for a car, van, truck, or whatever. This is DC, but it works the same for AC in your house. So you have a certain amount of amps. You cannot pull more than that certain amount of amps. It trips the breaker. Now, in a vehicle, what would be limiting the amount of amps coming out? That's going to be your alternator, right? Most cars nowadays got an alternator with a little wheel on it, which runs to the motor. The motor powers the alternator sends that power into the electrical box where it then splits out and goes to all your accessories in the car. In an RV, that might be a solar panel going in and doing that instead. In a home, that 60 amps is coming from your utility. Okay, so let's talk a little bit more about solar panels and batteries when it comes to amps. So we have 3 500-watt solar panels here. Each one does 50 volts at 10 amps. We have a solar charge controller, and we have a 12-volt and a 48-volt battery. So a higher voltage solar panel array will require smaller, cheaper cabling to run longer distance. And MPPT solar charge controllers favor high voltage. I know for some reason it still dumbfounds me that a lot of people like to run their solar panels in parallel, which means they hook the positives and negatives together for all 3 panels, and then they run that to their solar controller, right? And then that sends the power out to the battery, which in this case, positive to positive, negative to negative. Now, since you're adding 3 solar panels together, the voltage stays the same, the amps get multiplied. So what's coming in is 30 amps. So if you do this, you're running 50 volts at 30 amps, and that's going to be 1500 watts. The problem is now you need to run 30 amp cabling. And that 30 amp cabling, if we remember, look at the chart before, say you have to run this 50 feet from the solar panel to your MPPT. Say it's 50 feet. All right, so you want to run it 50 feet. You're going to have to do 30 amps. So you're going to need 2 gauge cable to run 50 feet at 30 amps. Okay, so what if instead we put these 3 solar panels in series, which is positive to negative, and then you actually take 1 cable, go there, and 1 cable, go there. So now what you do is you add the voltages together, so it's 150 volts, but you don't add the amps at 10 amps. So you're still getting the same 1500 watts as you got before running them in parallel, but this time it's only running at 10 amps. We're going to stick to 50 feet, okay? Go back to the Ampacity chart, and this time, instead of 30 amps, we only need 10 amps. And that means we can run 6 gauge cable. So big fat 2 gauge cable if you want to run 30 amps, or only 6 gauge cable running 10 amps. 6 gauge cable metric is 16. I don't know if that's millimeters. It doesn't say on here. But 2 gauge cable is 35. So my guess is it's probably about twice as thick as 6 gauge. 16, because you know, Europeans doing your metric are a lot more logical than we are. So 16, 35, I might have to guess it's probably about half this actual thickness of the cable. And AWG stands for American Wire Gauge, so yeah, this is what we use in America. It's not what's actually used in other countries. Let's go back to our chart, because there's something else here that's actually pretty important that you understand before we end this video. And a lot of people get confused by this. Your solar setup that you have here, so say you have a 60 amp solar charge controller. Now, that 60 amps depends on the battery voltage, not your solar voltage. People get this confused all the time. They go, well, it's a 60 amp controller, and I'm going to be putting 30 amps of solar panels into it, so I'm good. No, it doesn't work that way. When they sell you a solar controller, say this is a name brand solar controller, they tell you it's a 60 amp, that's 60 amps coming out into your batteries. So guess what? You guys already learned the equation about volts times amps equals watts, right? Well, you can run it backwards to figure out 60 amps in the volts. How many watts of solar could you pump into this if you change the battery voltage? Because your MPPT controller is based on your battery voltage. So at 12 volts, 60 amps, you're only going to be able to do 720 watts of solar, because you run this to your 12-volt battery from your solar controller, only 60 amps could go into that battery. So 60 amps at 12 volts. You can only have 720 watts. Now you have 1,500 watts of panels up here. What's going to happen? Since you're going to a 12-volt battery, you're now limited to only 720 watts. You're literally throwing away half of your solar because you decided to run it into a 12-volt battery instead of something higher. Now, you learned in the last video about voltage and why voltages in batteries make a difference. So you can refer to that video if you don't understand what's going on here. But say you want to pump this 60 amps into that 48-volt battery. Well, that's 4 times as much, because 48 volts is 4 times 12. It's 4 times larger. So if you pump it into a 48-volt battery, it's actually 2,880 watts. So all your 1,500 watts will go in and go into your 48-volt battery with room to spare, because you can pull as much as 2,880 watts into that battery with a 60-amp controller. In this case, you could add more solar panels, where in the old case with the 12-volt battery, 720 watts is the maximum no matter how much solar you provide. So it's always better, if possible, especially if you're running a larger inverter, to go with 48 volts. If you're running a small inverter in a car, truck, van, or RV, 12 volts is fine, because you're not going to have, in most cases, thousands upon thousands of watts of solar on the roof of your RV anyway. You're probably going to be limited to 1,000 or 2,000 watts total, in which case a 60 amp controller will work. Maybe you want to go to in between and do a 24 volt system instead of a 12 volt. That's up to you. Just be aware of the limitations. If you decide to go with a 12 volt system compared to a 48 volt system, now the 48 volt system has its own issues because most things in a vehicle require 12 volts to run, not 48, so you have to do step down conversion and all this other stuff you got to add in. Inverters for 48 volts are also more expensive. So that's why most people in vehicles stick with a 12 volt system. Okay, now that you're an expert on amps, part 3 is going to be about watts and watt hours. I'm also going to go over more detail about hooking up solar panels in series and parallel. I'm going to do that in a completely separate video. So be sure to subscribe if you're not a subscriber already, and ring that bell and check all notifications so you will be notified when these new educational videos drop. Thanks for watching. Till next time.
Odin commands you to like and subscribe, and clean my litter box.